him. Kill the guy now. You have to come. What? What is this? Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense on you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough like you'll be fighting kung fu in your dream. That's the reason why you have F's in your courses like especially made for you.
I have you last semester.
We by pounds on you. Very stupid. Oh yeah, change that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
Good day, everyone. Now, in the continuation of TH201 online lecture, we have started the test for convergence for the last 2 weeks. There are 4 of the tests, but we have discussed 3 of the instruments for testing the convergence of a series. We discussed integral test, the Lambert test, end-through test, and today we want to go to Leibniz test. Leibniz test, which is the 4th one and the last of the test. And we have that 4th one is Leibniz test. Leibniz test can also be called alternating test. And that one comes from one type of series, the alternating series. I think somebody will remember here. Don't forget, we have defined alternating series where we said A1 minus A2 plus A3 minus A4 and so on and so forth like that. That will give us the sum of n is equal to 1 to infinity over minus 1 raised to power n minus 1 an. And or 1 plus A2 minus A3 and so on and so forth, that will give us n is equal to 1 to infinity over minus 1 raised to power n of an. So that is how we define alternating series, if you remember. And having done that, we want to test for any series given to us. It will look like alternating series, but some other things, this an, don't forget, this an may be fraction, this an may be exponential, anything. But this thing will make it look like alternating series in its definition of the question given to you. But what Leibniz says, if you have a series and you want to test for its convergence. Now, Leibniz says if you have, there are 2 conditions. If you have the absolute value of an plus 1 that is less than equal to an. If you have this one, and the second one is that if the limit of n tend to infinity in an is equal to 0 for n greater than equal to 1. Yes. If you have 2 conditions satisfied, then you say the series is convergent, or that Leibniz test. Don't forget, this one give us, if you remove this absolute value, then this one is talking about it's talking about decreasing sequence. If this one is not there, then strictly decreasing sequence. But if I remove this absolute value now, just the absolute value, and it remains this and this brother. And this symbol, it will change to decreasing sequence. But if at decreasing sequence, in absolute value we have this, and this condition is satisfied, then the series is convergent under the Leibniz test. Now, let us discuss an example and see the application. Example 1, using Leibniz test to test convergence. To test the convergence of the series. The series is given as n is equal to 1 to infinity over minus 1 raised to power n minus 1 over 1 plus 2 raised to power n. That is the question. Yes, we want to test the convergence of that series. The first thing we need to do is to look for the value of this. The value of this. But don't forget, this value is this brother. Then if we can tell that the value of this is less than this value, then we are done. We are done. Let us go for that. Solution. If our AN, now let me put absolute value, is equal to minus 1 raised to power n minus 1 divided by 1 plus 2 raised to power n, now in the absolute value, if I have that one. Then after this, don't forget, this one can go for this. Okay. Let me write it in law of indices. In law of indices, this one can be written as minus 1 raised to power n multiplied by minus 1 raised to power minus 1 divided by 1 plus 2 raised to power n in the absolute value. Yes. But don't forget, from this brother, this one will be equal to 1. Forget about negative 1 or something. 1 raised to power minus 1 is 1. Yes. Because this absolute value, even if this one will give us negative, it will change. This negative absolute value will change into a positive number. Now, in that case, this one will remain minus 1 raised to power n divided by 1 plus 2 raised to power n. That's what we are going to have in that one. Then, after that, if I want to use this absolute value, whatever the value of n, now listen. If n is odd, don't forget the value of this one will be negative. If n is even, the value of this n will be positive. Now, it means I can have negative values if this absolute is not there. But forget about the absolute value now. Sorry, about the negative now because of the absolute value. So, the value, the positive value that this one can have is 1 raised to power n over 1 plus 2 raised to power n. And that is absolute value of an. We'll keep that one. Let me call this one equation 1. Now, what is absolute value of an plus 1? It means wherever I see n, I want to add 1. It will be increased by 1. Then this one will give me minus 1 raised to power. Look at this one. N plus 1 minus 1 will give me n. Divided by, this one will give me 1 plus 2 raised to power n plus 1 in the absolute value. If that is the case, then this one will give us minus 1 raised to power n divided by 1 plus 2 times 2 raised to the power n. Or, no, let me, even 2 raised to the power n plus 1. Let me leave it like that. 2 raised to the power n plus 1. What is there is that, don't forget, I want to have the partial sum of my n from 1. Here, if my n is 1, this one will be raised to the power 2. If my n is 2, it will increase like that. Then, this one can simply be 1 raised to the power n over 1 plus 2 raised to the power n plus 1. Now, this is where we are going. This is where we are going. How are we going to determine from 1 and 2, from this 1 and this 2, which one is the greater? Which one is bigger? Now, look at it. Don't forget, let me just divide our memory. 1 over 2 is strictly greater than 1 over 3. As the denominator increases, then the fraction supposed to, the value reduces. Now, in that case, it means if my n is 1, here I will have 1 over 3. 1 over 3. And this one will be 1 over 4. No, is it 4? This 1, this 2. This one will be 2 now. 2 raised to the power 2 will be 4 plus 1, 5. I will have 1 over 5 here. Don't forget 1 over 3 is greater than 1 over 5. If n is 2, this one will be 5. This one will be 7. This one is greater than this. You can see that every value at each point, the value of this will be greater than this. It means the absolute value of this is less than the absolute value of this, which satisfies the first condition. Now, from 1 and 2, it can be easily seen that an plus 1 is less than or equal to an. Yes, it's less than or equal to an. Now, let us test for the second condition. Now, the next thing is that I want to take the limit as n tends to infinity in that absolute value. I know the absolute value of an. Also, limit of n tends to infinity. So, I want to take the limit is equal to, I know this brother already, which is limit n tends to infinity of 1 raised to the power n over 1 plus 2 raised to the power n. Good. If this n tends to infinity, look at this brother. Whatever raised to the power 1 raised to the power n, it will be 1. Forget. This one will give us 2 raised to the power infinity. Then it will give us infinity. 1 plus infinity is infinity. Then 1 over infinity, we approach 1. So we approach 0. So in that case, this brother is simply equal to 0. Thus, the series convergence. So the series convergent. Yes, that's how to test for Leibniz test. How to test, use Leibniz to test for the convergence of a series. Okay, for the meantime, let us go to absolute and conditional convergence. And that will be the last section in that topic. Yes, I think so. Okay, let us go to absolute and conditional convergence. Yes. Absolute and conditional convergent. When we use a series, it's convergent absolute. When we use it's convergent conditionally. If I have this series as n is equal to 1 to infinity, yes, if I have this series, then I will say this series is convergent absolutely. It's convergent absolutely. This series will be convergent absolutely if n is equal to 1 to infinity an. Can you see? The absolute function of this series, if the absolute function of that series is convergent. If the absolute is convergent. But this thing will be convergent conditionally. It will convergent conditionally. Okay, it's convergent conditionally if to infinity is convergent. But this brother, this absolute value is divergent. Yes. If the absolute, yes, if you test for this thing and this is convergent, but the absolute value of that function of that series is divergent, then you say it's divergent conditionally. It means there are some condition for it to be convergent. There are some condition for it to be convergent. Yes, there will be a theorem there. Yes, just by the theorem. It's not so for here. But let us look at a problem. Yes, we look at a short problem. When we solve the problem, you see how it looks like. Example. Show that the series n is equal to 1 to infinity minus 1 raised to the power n minus 1 over n converges conditionally. Yes. We want to test if that series converges conditionally. Condition. What are the conditions at which it will not be convergent? Solution now. Let our an be minus 1 raised to the power n minus 1 over n. If I put my an in that form, and don't forget, let me give my n to be 1, 2, 3, and so on. Then I will say my n is from set of natural number. My n is the set of natural number. It means n can never be equal to 0. If n is 0, this function will be undefined. Then it will be undefined. Now, if n is 1, this one will be 0. Yes, I can have it 0 over 1. 0 over 1 is a follow. 0 over 1 will give me 0, and so on and so forth. Then, that condition is good for us. Now, it follows that let me now say the summation of n is equal to 1 to infinity is equal to the summation of n is equal to 1 to infinity of minus 1 raised to the power n minus 1 over n. Yes, that is the summation. Then what will be the sum? at my n start from 1. If my n is 1, I've said it. 1 minus 1 will be 0. Minus 1 raised to power 0 is 0. Over n is 0. Plus, if my n is 1, it's 2 now. This, 2 minus 1. If I have 2 minus 1, no, this one will be 1, no, this one will be over 1. If I have 2 minus 1, then it will give me 1 over 2. Minus 1 raised to power 1 over 2. So if I do all the sum will not give me this. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on and so forth. But if I look at that value, let me see. There are some things I don't believe there. Because this one's supposed to be alternating series. Yeah. Let me just look at it. If I have my n to be 1 now, minus 1 is the power 1 will be positive. So this one will be 1 minus 2 plus minus like that. So that's how it's supposed to be. That's how that one's supposed to be. And this one, let me call it equation 1. That's how one's supposed to be. It will be alternating series. The question. Now, I want to find the absolute value of that function. The absolute value of that function. And the absolute value of this brother. The absolute value of that brother is equal to n is equal to 1 to infinity over minus 1 is power n minus 1 over n. Yes. But all this one, don't forget, it will give me the same value there. But there will never be negative because of this absolute value. Then this one will give me 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. That is where positive is supposed to come from. And it will continue like that to, let me call this one equation 2. Now, look at this series. This series will continue to increase. It will continue to decrease, until it gets to a point where it will terminate at infinity. It means this function is divergent. This one is divergent. But look at this one. It's alternating. I don't know which one. Is it going to give me positive infinity or negative infinity? It means this function, there will be a place where it will be 0. Then it will give us, it is a divergent series. This one is divergent here. You can see that this is an. The an is divergent, but the absolute value is, this an is convergent, but the absolute value is divergent. Then at that case, then this condition, if the conditionally is satisfied, if this one is convergent and this one is divergent. So I will write my last statement. I will say from 1 and 2, 1 is convergent, it converges, and 2 is diverges by Leibniz test. It's diverges by Leibniz test. Therefore, the series n is equal to 1 to infinity minus 1 to the power n minus 1 over n converges conditionally. Converges conditionally. And that is the end of the problem. Yes, we are done with section 2, chapter 2 of that textbook, and that is all about the sequence and series. The next topic is partial differentiation, and we meet to discuss that one later. God bless you all.
Finish him. Kill the guy now. Grab the gun.
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
Who is King Kong, sir?
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you'll be fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have V last semester.
We by pounds on you. Very stupid though. Yeah, change that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.